So let's pick up where we left off last time. If you remember last time, we were looking at the Gibbs free energy as a function of composition in a binary alloy, and we looked at the entropy of mixing, assuming that's sort of a random alloy, and showed that, of course, mixing always increases entropy and therefore always reduces the Gibbs free energy when I have a mixture of A and B. And then we also looked at the enthalpy of mixing using the quasi-chemical approach of just sort of counting nearest neighbour bonds. And of course there are two cases there where it could be an endothermic mixing because AB bonds are less energetically favourable than AA bonds and BB bonds, and so mixing costs energy, or where it could be exothermic and actually mixing is also energetically favourable. And we saw that in the case of a regular solution, actually the enthalpy of mixing takes a particularly simple form where it's a constant times the concentration of A times the concentration of B. Okay, it just took that very simple form. And what that meant was, at high temperature, entropy always wins because it, F equals H minus TS. So if T is large enough, S will always win out. So you'll always mix at a sufficiently high temperature. And in the case of exothermic mixing, where mixing is energetically and entropically favourable, of course you'll always mix as well. But there's an interesting case when mixing is energetically unfavourable, when it's endothermic, and when you're at sufficiently low temperature that entropy doesn't dominate, where you get a scenario where there is a distinction between a range of concentrations where mixing is favourable. Mixing is always favourable for very dilute mixtures. When one of the components is very dilute, you'll always get mixing at the extremes of concentration, but in the middle there's this miscibility gap where actually mixing doesn't happen, and so energetically, thermodynamically, the system wants to separate into two different components with different compositions, and we looked at that. And then at the very end we actually got on to what the course is supposed to be about, which is kinetics. And we saw there that actually you can distinguish between regions of the composition space where that separation into two phases occurs spontaneously without any mixing. That's where the Gibbs free energy curve versus composition is concave down, so the curvature is negative. And under those circumstances, you get something called spinodal decomposition. And then outside that region, where the free energy versus composition curve is concave up, although separation still wants to occur, it will not happen spontaneously. It requires nucleation to occur, and that is an activated thermal process. And so the kinetics are very different between those two regimes. In both cases, the system always wants to separate into two components with different compositions, but in one case it will do so spontaneously, so it's sort of instantly, and in the other case it requires nucleation, so it's a thermally activated process. Okay, right. Today we are going to start by thinking about chemical potentials. So, again, something that I think you have met in the equilibrium course. Is that correct? I'm looking for some nods of understanding. Okay, so the chemical potential, and I'm going to again do this in the context of our binary alloy. So the chemical potential of component A is a function, in fact, of external conditions, so pressure and temperature are generally what we're interested in here. They're usually the things that will be being held constant. And it will be depend upon the amount of A and the amount of B, so it depends on the composition of the system. And it's defined as a partial derivative of the Gibbs free energy with respect to the number of atoms of A at constant pressure, temperature, and number of B atoms. In other words, if you like, it's how much does the Gibbs free energy increase when I add one atom of A, because that's the smallest change I can make, right? So I add one atom of A, how much does the Gibbs free energy change? Now, of course, that means that this G here is not the G that I was talking about last time, which was a molar Gibbs free energy. Because, of course, if I start with Avogadro's number of atoms in my system and then I add an extra A1, I've now got Avogadro's number plus 1. But that is what that derivative is, and therefore I'm going to put a prime there to say that actually this is a total. We're not talking about molar Gibbs free energies here now. Okay. If I were talking about molar Gibbs free energies, then it would be a little bit different. In order to add an atom of A, I'd have to remove an atom of B, and then actually the change in the change then would be not just the chemical potential of A. It would be the chemical potential of A minus the chemical potential of B. It would be we'll see that a little bit later. In other words, so the chemical potential is how much free energy does it cost to increase the number of A atoms in my sample. And of course, you're familiar with this expression. Generalized first law for the total differential of this Gibbs free energy. So S primed and V primed are the analogues. They're not molar entropy and molar volume. They are now total entropy and total volume for this particular system that I'm thinking about. So now let's consider, okay, for a given composition, let's do a thought experiment now. Remember, a lot of what I do in these lectures is thought experiments. They're not supposed to describe what would really happen in reality. But imagine I want to create my alloy A1 minus X, BX, okay, at fixed pressure and temperature, okay, and I'm going to do it and composition. Okay, what's that mean? That means, e.g., if I had, let's say, XA is 3/4 and XB is 1/4. So these are now the concentrations or the molar fractions. Okay, XA and XB. I'm going to try and make a mole of an alloy with a given composition like that. So that, in other words, that would be known as A3B. That's how you'd write it stoichiometrically. Okay, so I want to make a mole of that. How would I do that? Well, I'd add. That would mean I would, at every point in time, I would take 3 atoms of A from my bucket of A and 1 atom of B from my bucket of B, and I would drop them into my bucket for the new alloy. And then take another 3 of A and another 1 of B, and I'd drop those in. And I keep doing that. Do you see? So I'm adding atoms to the system, but always in the same ratio, such that the composition of the alloy that I'm making is staying the same. And I'm doing that under constant pressure and constant temperature. So in this expression for my differential for the Gibbs free energy, you can see dt and dp are naught. And in fact, dNA and dNB are related by a fixed amount, right? So in this circumstance, dg primed is going to be mu A times, we could actually say XA dN plus mu B XB dN, where XA and XB are just those fractions, 3/4 and 1/4, and dN is the number of formula units, A3B, that I'm adding. Okay. And that tells me, if you imagine now integrating that, so XA and XB are constants here, mu A and mu B are constants because everything they depend on here, although I said they depend on Na and Nb in a way that's, they depend upon the composition of the alloy, is what I really mean by that. Okay, so those 3 things are staying constant as I'm doing this, therefore mu A is a constant. The chemical potential of A at this pressure, at this temperature, in this alloy with this composition. Okay, that's what mu A is here. That is a constant, so I can just integrate that up. I can just integrate that up until I have a mole of the stuff. Okay, and therefore, actually what that tells me is that my molar free energy is mu A, which is a function of composition, let's say, times XA plus mu B XB, type that. Okay. All right. So what I've done is I need to be careful now about exactly what I mean here. Initially I defined it sort of in terms of the total number of atoms. Here I've sort of slightly rescaled. There's when I've integrated up dN, I've probably gone to Avogadro's number, and I've kind of included Avogadro's number in the chemical potential now to make a molar chemical potential. Okay, so in other words, this chemical potential is to do with the rate of change at adding a mole of atoms rather than that. So let's just make sure that's absolutely clear that we're talking about molar quantities now. Okay. So note that I've been quite careful here to be explicit about the fact that the chemical potential, okay, it depends on the external conditions, pressure and temperature, but importantly it also depends upon the composition. Okay, the chemical potential of, let's say, carbon in steel is different from the chemical potential of carbon in graphite or carbon in diamond. Okay, and I'm trying to capture that, and you'll understand a little bit later why I want to do that. Now, let's remember our ideal solution. Remember our ideal solution. Our ideal solution was where there's no energy change on mixing. There's only an entropy of mixing here. And last time we showed that the molar Gibbs free energy can be written as this. It's the molar Gibbs free energy for pure A times the fraction of A plus the molar Gibbs free energy of B times the fraction of B, and then there is the term from the entropy of mixing, which was that term there. Okay, and if I compare these two expressions, okay, then they must be equal, and that tells me that mu A is GA plus RT log XA, and mu B is GB plus RT times the log of XB. Right, let me try and draw this now. So let's draw a diagram where I've got 1 and 0 for the molar fraction of B. So as ever, we've got pure A on the left and pure B on the right, and I'm plotting Gibbs free energy up the axis, and I'm going to plot, there's the Gibbs free energy of pure B, here's the Gibbs free energy of pure A, here's the curve for our ideal solution, like that, and I'm going to assume that we're at some, here's our composition of the alloy that we've made, let's say somewhere in the middle there. Okay, so the Gibbs free energy is there, Okay, so that is a plot. The green plot is a plot of this line, this curve. Okay, it's valid at all compositions. This is something that gives me the Gibbs free energy at that composition in terms of these things. Now, this equation, if I write xb as 1 minus xa, okay, and I treat these as constants, then that will be a straight line. Okay, and it must agree with it. These two must be equal at that point. So what that means is that this is actually the equation of the tangent to the green curve at the point of interest. Like that. Okay? Okay, do you see that? This is the equation of a straight line. This is equation. This equation is valid at all values of xa and xb. This equation is actually only equal to the molar Gibbs free energy at the composition I created the alloy at. Okay, so that's only at that point. At other points, the only reason that it would trace, these two would trace, is that because actually mu A and mu B are not constants. As you change the composition, you change the chemical potential, and that's non-linearity in there is what would enable you to trace out the green curve. But if I treat them as though they were constants, then this is the equation of a straight line, and it is the equation of the tangent. But it is quite useful because you can see for pure A, where xa is 1 and xb is 0, then G is mu A at xa. Okay? In other words, down here is mu A. That intersection of the tangent with the y-axis at pure A is the chemical potential of A at the composition marked by the blue arrow. And likewise on the other end. Okay? Okay. Now we know from our expression that actually mu B is GB plus RT log XB. Do you remember that XB is always between 0 and 1, so its log is negative? So actually this term is negative, so that's why mu B is below GB there, and mu A is below GA there. But it also actually means that on this, that distance, if you like, is minus RT log XB, and that distance there is minus RT log XA. Is that okay? Any questions about that? Can you see what happens as this? Can you imagine now that this blue point, this blue composition, let's imagine that we were to move that left or right along the green curve. As we move it to the right, the tangent is going to get steeper. So mu B is going to increase, and mu A is going to decrease. Okay. And we might think, why is that? Well, that's because as we move the blue point to the right, the alloy is getting richer in B. So A is becoming less dilute. Is becoming more dilute. Okay, so mu A is the change in order for us to add more A, to make A back up towards its original concentration. And you can see that here that's right, because if we move the blue thing to the right, the free energy is increasing. So we're adding B atoms, we're increasing the free energy. It's saying, well, hey, if you add A atoms, it would come back down again. As the blue point approaches the right-hand side, pure B, remember this thing about the logarithmic derivative, the fact the slope becomes infinitely steep, but actually the value doesn't diverge. Then actually what happens is you see that mu B would actually coincide with GB. That's what the equation also says. Here, when XB is 1, then those two things are equal. In other words, another way of thinking about the Gibbs free energy for pure B is actually it's the chemical potential of pure B, which I might call mu B with a 0 there. So that's pure B, and this one here as well is pure A. Okay, but in between, because of the entropy of mixing, actually it doesn't cost as much to add A or B as it does to take an atom from, as it does to put an atom in pure A and pure B, because the entropy of mixing is positive, therefore the free energy of mixing is negative, so you kind of get energy back. A atoms, if I've got very rich AB alloy with lots of B in it, adding an A atom to it, well, that's great because that creates lots of entropy, and that releases free energy. So it doesn't, putting an A atom in there does not cost as much energy. Okay, might need to come back to that, but for now let's go over here. Now, the next thing we discussed last time was the regular solution. Okay, and remember this was the one where we had the particularly simple form for the enthalpy of mixing, which was omega times XA plus XB, and then we had the same term for the entropic contribution as before, like that. Now, let's try and find mu B from this picture. One way that you could find mu B would be to take the value of the Gibbs free energy at that composition and then add, and then use the fact that this is the tangent, so you know the slope of this. Is it clear? The slope of the red line is mu B minus mu A. Is that obvious? This difference in the endpoints in the y is mu B minus mu A, and this is 1. So the ratio is mu B minus mu A. Yeah?
So the red line is derived from molar G, just substituting xA for 1 minus SB.
Yes.
And molar line, the green one. Oh.
The green one is now this expression here that we got last time for the molar Gibbs free energy. Yeah. Okay. For them to be equal, the chemical potentials must do this. Yeah. But the red line comes from treating, but by saying I'm going to treat mu A and mu B as constants, right? And then if I plot it out, I would get the red line. And so the meaning of this mu B here, this section here, is that's the chemical potential of B at that composition. As I move the composition, that point the tangent will steepen, that point will move up, and therefore mu B is changing. Right? Mu B is a function of composition, but to plot for the purposes of just plotting that red line, I treat it as a constant. I'm sorry, it is a bit confusing, but that's how to graphically interpret it. So I could calculate this intercept here by starting from this point, saying I know it's got this Gibbs free energy, and then multiplying the gradient of this straight line by that distance there. That distance there is 1 minus xb. Yeah. So let me just write that down. So mu b is g. Whoops. Is the Gibbs free energy at concentration xb plus that distance along the x-axis times the derivative of g. This is a slightly strange calculation we're doing. Just bear with me here, okay? Do you accept that's just looking at that graph and the geometry of that straight line, working out where the intercept for mu b is going to be. Let's just write down what that will be. So that just means writing down the equation above. So that's the first bit, g of xb. And then adding on to that, 1 minus xb, which is also known as xa, times the derivative of this expression with respect to xb, remembering that xa plus xb is 1, so if I take a derivative of xa with respect to xb, I get a minus 1. So I get, what that means is I get minus ga plus gb, and then this is a quadratic term from which I actually get that. This is a good thing to check out later yourselves if you want to, and then plus rt times the derivative of that, which it turns out is log of xb minus log of xa. Okay, I will let you do that later. What you see is I've got gaxa here minus gaxa there. So those cancel out, and here I've got gbxb and gbxa. xa plus xb is 1, so those two terms combine to give me gb. So we've dealt with that term and that term. There's two terms in there's terms in omega which go like let's write it all in terms of that. So it goes like 1 minus xb from the top upper line, xi times xb plus 1 minus 2xb. Leave it like that for now. That's ticked that and that. There is rt xa log xa here, rt xa minus log xa here, so that cancels with that, and here I've got xb log xb plus xb xa log xb. So again, those two combine, okay, which is gb plus omega. Here I've got xb minus xb squared plus 1 minus 2xb, so I've got 1 from there, minus 2xb, so I've got minus xb minus xb all squared, and I just think I've made a mistake there because I've forgotten the xa from there, which should be 1 minus xb times that there, so actually that's not what that is at all. That works out to be 1 minus xb all squared. You can do the algebra better than me probably like that. So in other words, we've got the chemical potential is gb plus rt log xb, which is what we had for the ideal solution, and then we've got the extra term from the regular solution, which is obviously slightly different. So obviously the enthalpy of mixing makes a difference. Before we go any further, let's just think about, finally then, real solutions. So, if the energy of, when we calculated the entropy of mixing, we assumed a random alloy. We used an expression for the configurational entropy, Kb log W, where W was the number of sort of states accessible to the alloy, isn't it? Which is kind of on the assumption that they're all got the same energy. But that's not true anymore. We've said that's not true. So that doesn't quite work anymore. And when we did the quasi-chemical approach to calculate the enthalpy of mixing, we also assumed actually a random alloy, that the probability of finding A atoms at the end of the bond, or an A and a B atom at the end of the bond, was kind of completely independent of whether that bond was energetically favourable or not, which is clearly not true, is it? So do you see, both of those bits of analysis we did in the last lecture both assumed a random ordering, which actually, when delta H mix is not 0, are not exactly true. So in particular, if delta H mix is negative, in other words, that means, remember, that mixing is preferred because AB atoms are preferred. What's that going to look like? Well, that's going to look like this sort. You're going to get this sort of arrangement, aren't you? You're going to get an ordered arrangement where, as much as possible, you're going to want to get AB bonds because they're energetically favourable to AA or BB bonds. So you'll tend to get ordering. On the other hand, if you've got endothermic mixing, so in other words, you don't want to mix A and B, they don't like to mix, then you're much more likely to get clustering. Okay? You're much more likely to have clusters of A and clusters of B. And again, that is not random either. Okay? And that's what, and so real solutions in practice, that's why they will differ from regular solutions. Okay? You can't go and find phased, right? If you go and find a phase diagram, you can look up phase diagrams online or something for binary alloys, real binary alloys. And of course, in principle, from the phase diagram, you should be able to kind of work out roughly what the Gibbs sort of free energy curve looks like, right? Or at least you could try and see if you could fit the phase diagram to that regular solution model. You can't do it. First of all, remember, everything we said about that said that the free energy change on mixing would always be symmetric about XB as a half. You'll never find that in a real alloy. Okay? So the analysis that we've done is useful conceptually to understand some of the things that contribute to what's going on, but quantitatively, in trying to actually match on, you won't find that it gives you an accurate description of any real alloy. Sorry about that. But there we go. So, we have got an expression for chemical potential, and we had one for the ideal solution, which was Ga plus RT log the concentration, or the molar fraction. And then we found that in a regular solution there was an additional term in omega. For a real solution, what we do is we delete that, okay, and we write this. Here's an equation. We give this a name. We call this the activity of A, and we pretend we understand it now. We don't, right? There's nothing happened here. All I've done is I've changed one thing called a chemical potential, and I've written it out in a formula where all of the nasty stuff here that I don't really want to think about, I now incorporate into this activity. Okay, so the activity is kind of not the same as concentration, but maybe it makes me feel a little bit better about it. Okay, let's just compare the regular solution again. So for the regular solution, remember we had mu A is Ga plus omega 1 minus xa all squared plus RT log concentration, and we're now saying that that is Ga plus RT log activity. Okay, so that appears in both of them, and we can rearrange this, and we can clearly see that the log of the activity over the concentration is omega over RT 1 minus xa all squared. So for the unrealistic regular solution case, we can write an expression for the activity in terms of concentration, and we can check, let's check, when omega is 0, that's the ideal solution. So no energy of mixing. Then the right hand side is 0. That means that the argument of log must be 1. So activity is the same as concentration. So that's what it means, okay? In the case of an ideal solution, where there's no energy of mixing, activity and concentration are just the same thing. If omega is less than 0, so mixing is favourable, that means the right-hand side is negative, and therefore that means that the activity is less than the concentration. And if omega is positive, which means that mixing is energetically unfavourable, then the activity is greater. Okay? Because it costs here less, whoops, I didn't mean to do that, press the wrong button, less there or more there to add atoms of A to the solution, depending upon whether it is exothermic or endothermic. Okay? Just to confuse things a little bit more, we therefore think, okay, so let's now, what have I got to on here? Let's now define something else called the activity coefficient. Call that gamma. Gamma A is the ratio of activity to concentration. Okay, so it's the thing that appears inside here. Okay, and it's just a way of saying, well, if in the ideal solution activity and concentration are the same, so the activity coefficient is 1, we can now measure the departure from an ideal solution by the departure of the activity coefficient from 1. Okay, so if I have so for a dilute solution of B in A, okay, so that is going to mean that XB is small. Let's consider that case. Okay, so we're close to XA is 1 and XB is small. Then we can write this. For B, because B and A are interchangeable here, there's the equation just for B. We've said that XB is much, much less than 1, so we can neglect it on the right-hand side, and therefore we get that, or the activity coefficient is just E to the omega over RT. Okay? And that's going to be constant in the sense that that's independent of concentration as long as we remain within the approximation where this is a dilute solution. Okay? That is sometimes called, I suppose it's Henri's law. On the other, so that's for the dilute component. On the other hand, for the component that is dominant, sorry, that would be, try not to confuse you here, so that would be our expression there, but 1 minus XA is XB, and XB is very, very small, yeah, because XA is almost 1, so the right hand side is close to 0, and that tells you that gamma A is 1, and that is Raoult's law, which will probably behave badly. Now what you notice about that, the activity coefficient there is close to 1, and 1 was what we had for ideal behaviour here. In other words, if I have a binary alloy which is very rich in one component, so it's almost pure A with a little bit of B, then the A component, the dominant component, actually behaves like it's ideal. That's no great surprise. Yeah? There's hardly any B atoms there. Most of the A atoms don't know that there's any B atoms in there. And pure A obviously behaves ideally because there's no mixing. So it behaves like an ideal solution. Whereas the B is not like that. B behaves slightly differently. Essentially for B, the B atoms are very, very dilute. So of course they're surrounded by A atoms, but they'll never meet another B atom. Highly unlikely that they'll ever meet another B atom. Okay? And therefore they behave to all intents and purposes as though they're the only B atom in the universe of this A-rich alloy. Yeah? So that means that it doesn't matter whether I have, if I've got Avogadro's number of atoms in my system, it doesn't matter whether I've got 10 B atoms or 100 B atoms. There's hardly any of them, right? They're miles apart from one another. And therefore, that's why their activity doesn't depend on their concentration in Henri's law here. Okay? Because they're never going to see, they just behave like they're an isolated B atom in a sea of infinite A atoms. And they don't know any different than that. If I were to try and draw a sketch just to sum this up, this is a nasty one to try and draw. Here again is this. Here is the activity. So I'm now looking at the activity of B, okay, against XB, where this is going to 1. So actually that would be pure B. Here is pure A. And let's draw a line on here, which is this one. So this is the ideal behavior, like that. Okay. And it turns out that if omega is positive, this will look as follows. That's if omega is positive. Remember, if omega is positive, we don't like to mix. The activity is greater than the composition, so the blue curve is above the green line. And it looks like that. It looks like that because down here it's got to be like a straight line, because that's Henri's law up there. It's got to obey Henri's law, where the activity coefficient, the tangent to this thing, is constant at low values of xb. But as we get close to b is 1, we're getting close to pure b, and b should behave ideally there. Therefore, it's got to asymptotically approach the ideal behaviour. Similarly, if it was exothermic, then it would behave like that. Okay. Any questions about that? So that's a bit about chemical potentials and activities, and so on. And got it? Right. So now I want to talk about diffusion. Because of course what we've talked about so far is all kind of hypothetical and lovely about chucking atoms in buckets and things like that. But in reality, you have a system of a fixed number of atoms, and all of the things we've been talking about phase separation and so on, can only occur by the various atoms moving around in the solid, so that you might preferentially create regions which are rich in A and other regions which are rich in B, for example. And the atoms are going to do that by diffusion. So this is one of the fundamental processes controlling the rate of phase transformations, because they are limited by the rate at which matter can move from one place to another within a material. So diffusion is what very often determines actually the kinetics of a phase transformation. And what drives diffusion? But again, it's to decrease the Gibbs free energy. That is the driving force for diffusion. So I'm going to now consider a case. Okay, here is again, I'm going to put two blocks of AB alloy together. Okay, this one here is rich in B. I'll call that block 1. And block 2 is rich in A. Okay, so I've made these separately. I'm going to squash them together, push them together hard. I'm going to heat them up to a high temperature. I'm going to leave them for a week or longer in order to allow long-range diffusion to occur. So atoms from 1 can diffuse into 2 and vice versa, like that. Now, if we go back to our diagram of Gibbs free energy versus concentration that you're getting sick and tired of now. Okay, here's pure A, here's pure B. So we've said we've got a B-rich, composition 1, and we've got an A-rich, composition 2. And let's take composition 3 as the one midway between the two. Remember what we did last time, we sort of thought about drawing this line between two. I'm assuming that the two blocks I originally had were equal, so half a mole each. Okay, so block 1 has this energy here and block 2 has this energy here. And it wouldn't necessarily be the case as I've drawn it here that they've got equal Gibbs free energy. That's an accident of me drawing this. Right, they might be different. But clearly, if I just squash them together and ask what is the Gibbs free energy of the whole thing, then it's just the average of the Gibbs free energy of the two. Okay, neglecting, because it's very small, any contribution from the interface between the two. Okay, there's the number of atoms involved in the interface is a vanishingly small fraction of the total number of atoms in the whole system. So, in other words, the Gibbs free energy of the combination of the two would be that point on the chord, the straight line joining the 2 points on the curve. Whereas if we know, if what happens is that B atoms diffuse from 1 into 2, okay, that means that, so we're now going to allow B to diffuse into there, and A is going to diffuse like that. Then you can see that region 2 is going to become more rich in B, and region 1 is going to become less rich in B, and those 2 points are going to come down and eventually will reach that point down there, which is lower in energy. So we see the general thing that we can lower the Gibbs free energy by eliminating the concentration difference between these two things. In other words, by this diffusion to occur. However, what about this case? I'm really going to have to try and be careful and do a good job here. Right, here's the case, low temperature, endothermic, where we start from here and here. So we've got those 2 points. Okay, there's the concentration in between. There's that one. What's going to happen now? Say what you see. It's always a good tip in science, is just to say what you see. Don't worry if it sounds stupid. What's going to happen to block 2, which is rich in A? It will become richer in A. It will move that way. Block 1 will become richer in B. Now, you weren't expecting that, were you? You thought things always diffuse to equalise concentrations, like in this case here. But no, that's not the case. Not if you're in a miscibility gap. In a miscibility gap, diffusion doesn't occur in order to equalise concentration. Diffusion occurs to actually drive a wedge between the compositions of two components and, if you like, almost increase the separation of it. This is sometimes called uphill diffusion. Okay? And it's uphill diffusion because it's diffusion in the wrong sense against the concentration gradient. Yeah, the concentration gradient is the thing that tells you how the composition varies with time, and normally you expect that diffusion flattens that out, but here it steepens it. So we could sometimes call it uphill diffusion. And of course the end point here would be when those 2 points reach the bottom, such you get a common tangent. That chord becomes a common tangent. as last time. Now, okay, let's just consider what's going on with the chemical potential here now. Is this going to work? Right. Let's just draw in the tangents. Here's the tangent for composition 1. Remember what that means? That means that this is the chemical potential of B in an alloy with composition 1. That's what the superscript 1 means. And here is the chemical potential of A in composition 1. Maybe I should put brackets around that. And then can I put this one on here as well? Oh dear, it's going to go a long way down there. I probably fudged that a bit. But there's the chemical potential of A in composition 2. And there is the chemical potential of B in composition 2. Okay? So what you notice is that mu B of 1 is greater than mu B of 2. The chemical potential in block 1, B rich, is greater than the chemical potential in block 2, B poor. So what do you want to do? Well, if I take an atom of B out of region 1 and put it in region 2, then that will give me a free energy gain of the difference between those chemical potentials. On the other hand, if I look at the A chemical potentials, the chemical potential of A in 2 is greater than the chemical potential of A in 1, so atoms will want to go from 2 to 1. That's the conventional situation that you're used to. Okay? And where will it go to? It will go until it reaches the bottom point, until the 2 points coalesce, and these 2 tangents will both become the single tangent at 3. At which point, the chemical potentials of B in both blocks will be the same, both halves of the block will be the same, and the chemical potential in block A will be the same. So diffusion will occur to equilibrate the chemical potentials across the system. Okay, that's the final position. Oh, crumbs. Right, here is the chemical potential of B in 1 and the chemical potential of A in 1, and here, fudging it very much with a wonky tangent so it doesn't go off the page, there is the chemical potentials in 2. And now it's the other way round. Mu B of 2 is greater than mu B in 1. That's why the B atoms want to get out of 2 and get into 1. And similarly, mu A1 is greater than mu A2. Again, the A atoms want to get out of 1 and into 2. But what will happen is that as those 2 points move apart, the 2 black points move apart, we'll get to the common tangent, and once we get to the common tangent, of course the common tangent is the common of the red tangents. So we will again achieve a situation in which the chemical potentials of A and B are equal in both parts of the system. Okay? In other words, the rule here is diffusion occurs down the gradient of chemical potential, not necessarily down the gradient of concentration, because those 2 things are not the same. They are not correlated, except in an ideal solution. In an ideal solution where there's only entropy, yes, diffusion always occurs down a concentration gradient. But actually, in general, it's the chemical potential and the spatial variation of the chemical potential that drives diffusion, not the spatial dependence of the concentration. And you need to remember that. And diffusion will cease, or at least net effects of diffusion will cease, when the chemical potentials are equilibrated everywhere. That's what you're trying to achieve. Right. Okay. Let's consider the motion of some atoms in a solid now. Okay, just zoom in now and try and understand what's going on. The atoms are jumping around at random. Thermally activated fluctuations, we'll think about this a little bit more. They may be jumping into interstitial sites, they may be swapping around, there may be some vacancies there and they're hopping into vacancy sites, empty sites, for example. But let's assume that there is some, but on top of that, there'll be some long-term net effect if, in the cases we're talking about, where atoms want to go from A to B or B to A, where there's some kind of drift that ultimately is occurring. Okay, it's a bit like electrons. You know the thing about electrons in a conductor. About you calculate the average speed of electrons, and it's massively fast, isn't it? At room temperature in a metal, and then you calculate actually the velocity that corresponds to a current that you might pass through a conductor, and you work out as millimeters per second. And the point is, they're rushing around like crazy, bumping into one another and doing all sorts of wacky stuff. But actually, most of the time, they're not going anywhere. There's a very small drift, which is sort of happening on top of that. Right, I'm going to define a flux of atoms as the number of atoms per unit area per unit time. Okay, in other words, you imagine that interface between the A and B blocks. Imagine I have a magic counter that can count A atoms as they go across that interface. Then the flux is the number of atoms per unit area of that interface per unit time crossing it. So I'm going to call that J. I'm going to put a subscript I for the species of atom. Okay, it's a vector quantity. It has the direction. Well, I'll explain this in a minute. And that's equal to the concentration. Okay, clearly the more atoms that are going to flow is going to depend on how many atoms there are in the sample to begin with. So I've got something here which is the number of atoms per unit volume, and then it's multiplied by that drift velocity. So can you see you've got something which is, you've got dimensions 1 over volume times some dimensions with length over time. Overall that's going to be area over time, which is what I said that this thing has the dimensions of. Okay, you just think about it. You just think about rigid translation. Okay, of the atoms of A with a given concentration, given velocity. That's how many will be passing per unit area per unit time. Now, that drift velocity V arises from some driving force, which we haven't specified yet. But we would write that the drift velocity is something is proportional to a driving force. Now, of course, that is not Newton's second law, is it? That is that's in the case where you've got drag. Okay, where actually you sort of reached, if you like, some sort of terminal velocity of this driving force because of all the scattering processes which are going on. In principle, this ratio here could be a second-rank tensor because your sample might be anisotropic. Okay, but what that means is that if I put that in here, then I get Ci times that tensor times the driving force. And we've said for diffusion, I have stated that the driving force is minus the gradient of the chemical potential. Chemical potential is an energy, so a gradient of an energy is a force. So that's dimensionally correct, and it better have that minus sign to get it going in the right direction. There could be a constant in there, a dimensionless constant in there, but basically there isn't. Okay, we'll just do that, and so that tells us that the flux is minus the concentration I think we'll drop we'll assume that's a scalar now. Okay, and this is sometimes called the modified version of Fick's law. Okay, let's just compare that to electricity. In electricity, the flux of charge carriers you call a current density. I'm going to use subscript little q to represent a species which is now a current carrier. Okay, Q is a charge. So it's the flux of charge now, and that is the concentration of charge times the drift velocity of the carriers, and the drift velocity of the carriers is related to electric field by carrier mobility, mu. Okay, so that's what that tensor is, and electric field, of course, is minus the gradient of the electrostatic potential phi, and so ultimately I end up with the flux is minus concentration times mobility times gradient of electrostatic potential, which of course these two things here, the product of the concentration and the mobility, is therefore the conductivity. Okay, and that's just a pointwise version of Ohm's law. Okay, so fixed first law. This fixed law of diffusion is just like Ohm's law, really. It's relating current, the flow of charge or matter here, to a potential difference or a chemical potential difference. That's why it's called a chemical potential, because it's essentially analogous to electrostatic potential, but just for motion. If you have heat flow, let's just do heat. For heat, you have the flux of big Q is now heat, is given by Fourier's law as proportional to minus a temperature gradient, and that's the thermal conductivity in there. It has a similar sort of form, although if you want to start sort of being really pickety about stuff, then actually the force in case of heat flow is actually minus the gradient of temperature divided by temperature. Okay, this is not anything to worry big time about, but just for the sake of completeness, and so I don't mislead you. Actually, that's the driving force for heat flow, and there's a compensating factor of temperature which is wrapped up into the thermal conductivity in there. Okay, the main thing at this stage is just to just modified fixed law. Okay, just where we've got to today. So we started by introducing the chemical potential, and we've done a little bit about extracting what the chemical potential is and what it means, and comparing it to the results we've got for ideal solutions, regular solutions. We've then had a look at how real solutions behave and considered this thing called activity, but we come back to then considering diffusion and showing that actually chemical potential is the origin of the driving force for diffusion. Okay, and that is captured in this modified fixed law. Okay, so kind of mentally hang that on a peg now, while I just tell you a few other things. I'm going to get about 20 minutes and then I think we'll have had enough. It is Friday afternoon, you're fed up, and I think I will have got far enough today. Just to talk about coupling of these things, which you may have come across before, but if you think about it, for example, if you've got a conductor and it's got electrons in it, so those electrons are at a temperature. So if you have a thermal gradient in a conductor, what's going to happen? Well, the hot electrons at one end, they're free to move. They'll want to diffuse through, won't they, to the cold end. But when they diffuse through, there'll be a current. So you see that actually these sort of driving forces we've been talking about, the flow of matter, the flow of charge, the flow of heat, they can be coupled together. Actually, heat, if you like, you could think about the carriers of heat as phonons, vibrational modes in the solid, they're normally responsible for the majority of the heat capacity in some materials. But they can interact, okay, and there can be momentum exchange. You know, electrons can scatter off atoms, electrons can be scattered by phonons. So there is a coupling between those, between the carriers of charge, the carriers of heat, and atoms as they move. So another way is, you know, no, maybe that's not such a good one. But imagine you've got a chemical potential gradient, and that sets up this drift velocity, this diffusive drift of atoms as a result of that. So if you imagine that you've got this sort of these atoms with this sort of slow drift with respect to the background. If they're colliding, if they're interacting with other things like the phonons in the system, then if I have something that's moving this way and something hits me, if you go into zero momentum frames and you do remember your collision dynamics or whatever, you remember it bounces off faster, doesn't it, than it hit me. Remember that? That's why if you're playing ping pong and someone, you know, that's why you make the ball go much faster by moving the bat. Yeah? So you'll see that actually, if all the atoms are kind of drifting through the material, and there are phonons going around as well, then actually the phonons are going to tend to actually start to take on board some of this drift. They're going to be bounced back faster, and depending upon their flux, they may start to move with me. So let me try and write something down to see what I mean. What do I mean? What I mean is that, for example, the flux of heat depends upon not just the driving force for the diffusion of heat, which is temperature gradient. It depends upon the driving force for atomic diffusion, charge diffusion, and also its own driving force. Okay? Remember, this is, what we mean here is chemical potential, electrostatic potential, temperature gradient. If I drop the vector thing just to keep us all sane, let's assume this is a scalar now. What do we mean by that? What we mean by that, well, I'm going to write this. Expanding about zero, right? When there are no forces acting at all, we're in equilibrium, there are no fluxes. So when the F's are zero, the J's are zero. So I can do an expansion. Okay, to first order. Just a first order Taylor expansion around nothing happening. Okay. And I could write similar equations down for the flux of charge and the flux of atom I. And in general, if it's linear, if in fact the relationship is linear, then in general you could write the following: that it depends like this, where L alpha beta is dj alpha by df beta. Okay, so those are just coupling coefficients. L alpha alpha would be an example of a direct coefficient, a coefficient between a particular flux and its own conjugate force, so between current and electric field, for example. But there are also these off-diagonal ones which couple the flux of one thing to the driving force of another. They're responsible for these cross effects. And by the way, Onsaga's principle says that that is a symmetric object there. Okay. But essentially all I'm doing here is I'm just writing down the general form of coupling. Let's consider an actual example. So let's take the thermoelectric effect. Who's heard of the thermoelectric effect? One? Okay. You're an expert in the thermoelectric effect? So thermoelectric, gradient in temperature produces a flow of heat and an electric field. Okay, actually. Or an electric field produces a flow of charge and a temperature difference across the sample. So let's consider a one-dimensional bar. It's an electrical insulator, this is. And we're going to impose a uniform thermal gradient. Temperature at each end is different. There are no other fields and there are no other fluxes. Okay? So the expression, if there is no driving force, so at the moment there's only a temperature gradient. Okay, so grad T only, no electric field. So our expression is just LQQ, and I told you that the driving force was that. And there we go, by comparing with Fourier's law, we see that thermal conductivity and that coefficient have to be related like that. Okay, because Fourier's law says the flux is minus K times grad T. Okay, so there's a bit of temperature dependence in that thermal conductivity. Okay, so that's an insulator. Okay, no current can flow. There's no electric field. Now let's consider a conductor. So in a conductor, we can have a electric field. So now we can have LQQ times FQ like that, and we can also have the same expression. Okay, so I write out my expressions like that. Now I'm not going to connect the ends. I've got a 1D bar, it's now a conductor, but the ends are isolated. They're not going to be connected together. Okay, so what does that mean? And the ends are also being maintained at these different temperatures. So there's going to be constant heat flow, but the flow of charge carriers is going to be zero, ultimately. Okay, there might be a little bit of redistribution initially, but there's no long-term. There can't be because there's no closed circuit here. So J, little q, is 0. And because of that, I know that the driving force for that must just be equal. Okay? In other words, this driving force here, electric field, minus gradient of the electrostatic potential, must equal minus that ratio of constants times that, okay, which is minus S grad T. It's a constant, well it depends on temperature, but it's a constant where S there is minus, and hopefully I have got that right. This is called the Seebeck coefficient. Okay. And essentially what it's saying is, look, there is the Seebeck effect, there is an electromotive force here, if you like. You can see that the temperature gradient, the driving force for heat flow, has created an electromotive force, a potential difference. Okay, and Seebeck coefficient is the thing that equates them. Now, if I go back over here, I can now substitute that back into JQ. JQ is now LQQ times FQ plus L big Q little q. So I'm writing out this expression here, but now FQ I'm going to insert from here. Okay, so little FQ there is minus L little q big Q, like that. Okay, which I can write as, if I want to, minus L q over T minus L, remember the symmetry by Onsaga's principle, L big Q little q is L little q big Q, sorry, not hold on a minute, I've already taken the 1 over T inside. I've already put F big Q as grad T over T with a minus sign, which is minus K prime delta T. Now, do you see, in the first example, the thermal conductivity there was just that. Now, in this case, the thermal conductivity, it's still obeys Fourier, it's still Fourier's law, but the thermal conductivity has been modified from its original version up here into something that's been corrected by this combination of these coefficients. So, okay, in other words, what we see happening is that in the simple example where there's sort of no coupling, no cross effects at all, you just have Fourier's law. But once you switch on the cross effects, then what you see is you see a clear coupling, okay, that actually the presence of one driving force can generate other driving forces as well. But you see that the Fourier's law in this case is still obeyed, but the conductivity is different because it depends upon the constraints on the other fluxes. Here in particular, that I've got an open circuit, so I'm not allowing current to flow. So that has led to a few charge carriers going from one end to the other, creating an electrostatic potential, an electric field. And that is actually modifying the thermal conductivity now, because it's having an effect on how things can move. So we exploit this in a thermocouple. Okay, now thermocouple works like this. I have a voltmeter. Okay, here is my thermocouple, and here is something I want to measure, and it's at temperature T plus delta T. And over here, where my voltmeter is, the temperature is T. Okay, and I'm going to have two different materials now, A and B. So there are two wires that are different, and they're joined together, and then that is a probe which is put into my sample to measure its temperature. Now, in one dimension, so I'm now going to do a sort of thing, a funny thing, where I now treat these wires as though they're just straight lines in one dimension. Okay, the gradient of the potential difference, so I'm looking at this equation here now. Okay, so that in one dimension is L Q big Q over T L little q times the temperature gradient. Okay, and essentially therefore I can eliminate that. Whoops, didn't mean to write that. d phi by dt is minus L. Okay, like that. And push comes to shove. What does that mean? Let's approximate that to delta phi over delta t. In other words, let's assume that delta t is small, such actually when I integrate up this differential equation here, I'm going to ignore that t dependence on the right hand side. Okay? It's a bit like what you often do with entropy and heat capacitors and stuff like that. You ignore the temperature dependence of the entropy when you're calculating it. And this is so actually, therefore, delta phi is minus S delta T. Okay, where that's our Seebeck coefficient again. And that's true whether we're in wire A, okay, or wire B. The temperature difference along both wires is the same, but the potential difference across both wires will not be the same because it depends upon the Seebeck coefficient that wraps up their cross-coupling. So the potential difference measured by the voltmeter will be the difference between these two, and will therefore be SB minus SA times delta T. Okay. Turns out the Seebeck coefficient is positive if your charge carriers are if your majority charge carriers are positively charged, negative if your majority charge carriers are negatively charged. But here you can see that your voltmeter will read something that is directly proportional to the temperature difference between your sample and your surroundings where your voltmeter are. The ratio of proportionality is the Seebeck the difference in the Seebeck coefficients of the two wires. So if you know what the two wires are and you've measured their Seebeck coefficients accurately, then this is a known quantity, and that's how you use a thermocouple as a temperature device. The Peltier effect is, if you like, the other way round. In the Peltier effect, you have the following. So I'm actually now trying to drive a current around a circuit where half of the circuit is made of material A and half of it is made of material B, and I've got some joints there. And what's happening is, remember that so what we're talking about with the thermoelectric effect is that current and heat transport are correlated. There's a coupling effect between the two. That means that the given current I, which is flowing both in B and in A, and assuming they've got the same cross-section area, the same current density, and so on, that's going to drag heat around with it. Now, B and A have different Seebeck coefficients, and so on. And it turns out that what's going to happen is that, look, if B is better at dragging heat around with its charge carriers than A, then you're going to be delivering more heat at this point to this point than A is able to extract. So you're going to have heat being emitted here into the surroundings because it can't all get carried away by the A wire. On the other hand, heat will be absorbed here. Okay, that's the Peltier effect. It's another thermoelectric effect. It's governed by a coefficient which is pi, which is the temperature times the Seebeck coefficient, and you can buy Peltier refrigerators. Okay, where essentially you have two different materials, you connect them up like this, you put this one goes inside your fridge, and this one goes on the back of your fridge connected to a big heat sink, and then all you do is you plug it into a power supply and you drive it. There's no motor, there's no freon gas or whatever gas is in, whatever is in your fridge this time being pumped round and continually condensing and evaporating to create it. You're just using this thermoelectric effect. So a lot of clever things in the world depend upon this. Other examples include so that's heat and charge, but obviously more relevant for us are charge when you've got ions diffusing through a material. So ions carry charge, don't they, as well as B being matter that moves around, and it will be no surprise that what happens is that the driving force for those is a combination of the chemical potential mu and the electrostatic potential phi, which is often known as the electrochemical potential. Okay, so obviously in an ionic material you put a voltage over it, the positive ions are going to go one way and the negative ions are going to want to go another way. It's pretty obvious, isn't it, that they're coupled, and that's just how you deal with that. Generally speaking, okay, there is something called the diffusion potential, which is just a grand way of wrapping all of this up into something sort of slightly vague. But the driving force comes from some potential like that. We will see later on how capillarity, surface tension, can affect diffusion potential. So if I have an interface like this, okay, where the curvature is changing sign here, then for atoms in here, phi is higher here than here, okay, because of the curvature of that interface. Material will tend to want to flow there. That means, because, and why is that? Because an interface costs energy per unit length. So what do you want to do? You want to flatten that interface out to minimise its length. How do you do that? You remove material from underneath that bump and you use it to fill in that dip there, for example. Around a dislocation, you have a stress field that varies in time. If you've got an edge dislocation, done those yet? Got a missing half plane of atoms somewhere. There's loads of space up there, but below the edge dislocation, you're trying to pack in an extra plane. If you've got an interstitial atom, where does it want to be? An extra atom. It doesn't want to be below, it wants to be above. Equally, a vacancy would want to be below because it relieves the stress, right? It relieves the strain down there. So you can see that the diffusion potential for a vacancy will be lower in a region of compressive stress, and it will be higher in a region of tensile stress. And so you can think about an elastochemical potential, okay, where actually a stress gradient is a bit analogous to a sort of electrostatic potential on an ion, for example, and the corresponding thing to charge would be the excess volume or some sort of volume effect that my defect wants to use. Electromigration is the final thing I'll mention. That happens in integrated circuits with very fine wires. We now know that as the current is passing through, as the charge carriers are passing through, we've also got some thermal effects going on, haven't we? And electromigration is now couple that to the movement of the atoms themselves. Okay, actually the atoms will be, their diffusion will be affected by this. There are current-induced forces on atoms. Okay, when you've got a current flowing through a material, the atoms actually feel a force which makes them want to diffuse. It arises from, anyway. Now, you can use that in one sense. You can sometimes use that beneficially to purify material by sweeping certain impurities through. Okay, apply a strong current. If the impurities couple to the current, they will tend to diffuse through and out of the material, and you'll end up with a pure material. But it's not very good if you've got a fine interconnect in your integrated circuit, and the atoms that interconnect is made of now decide that in response to this heat thing, they are going to diffuse. Because what's going to happen where they diffuse? There's going to be less atoms left. You're going to get a narrowing of the conductor. What happens when you narrow the conductor? The charge density goes up, the heat emitted goes up, you make the effect worse, and so eventually you get a break. So sometimes electromigration can be responsible for the failure of integrated circuits. And again, it's a result of a cross-coupling effect. Okay? All right, that's over then. Okay? So that last bit about coupling, there is a question about it on the first question sheet. The second question is about the Peltier effect, I think. And we will come back to the capillarity thing when we look at the stability of solidification frontal later on, but we'll come back and we'll deal with it more properly then. Okay? But the other things are more for your general education, and because you should know about these things by this stage. And actually because, let's say, like electromigration and things like that are really important for materials and devices you make from them, how well they work. Okay, have a good weekend.